Electron beam evaporation deposition is used to deposit thin films of metal and some of the oxides. This thin film deposition system comes under the category of physical vapor deposition, in which the employed material is physically removed from source by evaporation or by sputtering and transported by the energy of vapor particles from source to the substrate, where they form thin films. In the thermal deposition system, the material is evaporated by resistive thermal heating, whereas in electron beam evaporation system, the material is evaporated by heating through electron beam. In the E-beam evaporation system, electrons are thermally emitted from heated filaments, and these electrons are accelerated by applying very high voltage, something in the range of 4 to 20 kilovolt, and these filaments are located outside the deposition zone. This is a precaution is taken because if that is in the deposition zone, it will create contamination. And a extra thing is done here, that a transverse magnetic field is applied to deflect the electron beam almost 270 degree in a circular arc, so that this electron beam gets focused on the earth where the source material is kept. When this electron beam falls on this source material, they instantly give their kinetic energy by interacting with the materials, and it gets converted into heat energy, and then this heat energy basically start increasing the temperature of the material, and the material melts and start evaporating. These evaporated materials basically gets deposited in the form of thin film on a substrate, which is kept just over the this beam hearth. This E-beam facility that we have at nanoscale research facility is basically from Hindhai vacuum system, which has a telemark E-beam gun, and this system is fully automatic, where it is possible to deposit the materials within an accuracy of 1 to 2 nanometer range, and very slow deposition is possible, and also we can make the deposition very fast by controlling the electron beam energy. In this system, it is possible to deposit the films in a multiple layer by using multiple crucible without breaking the vacuum. So the system basically has a Inficon SQC 310 film deposition controller, which is possible to automate the whole process, and we can deposit the multi-layer without breaking the vacuum. The real-time monitoring of the deposition is also possible using this thickness controller. The another interesting point in this system is that the substrate temperature can be controlled. It can be heated at a high temperature, and we can go up to 360 degrees C, or it can be even cooled down by using liquid nitrogen vapor, and then it is possible to deposit thin films even at low temperature. So we have a IR heater here, which is used for heating this one, and the liquid nitrogen can be used for cooling down the substrate temperature. So there is a lot of advantage in using this E-beam deposition system as compared to thermal deposition or sputtering deposition process. The most important advantage in this one, that since there is a direct transfer of large amount of energy into the source material, it is possible to evaporate the material and dielectric materials which has a very high melting temperature, and such as molybdenum or silicon dioxide, which otherwise is not possible in using normal thermal deposition process. The other advantages in this technique is this: it can provide a very high deposition rate. As I said, described that it's possible to make or increase the electron energy, and then it's possible to deposit the materials with a high deposition rate. And since the energy is given controlled way to the material itself directly, this reduce the cost of the material wastage, because the hearth is not heated. The temperature of the hearth is kept at a room temperature or a lower temperature, whereas the material temperature can be increased to very high temperature for melting the material. Another advantage in this process is that it is possible to deposit the multi-layer structures, and also the very slow deposition rate is possible. One can grow films very precisely into 1 to 2 nanometer level in a very precise way.
This is our E-beam evaporation system. Now I am going to show how this system operates, and this system is inside 1000 class clean room in order to protect from the contaminated dust particles. It has two main units. One is the deposition chamber and another is the control unit. So let's first try to understand what are the different parts inside the deposition chamber. Now let's open the deposition chamber. This is our deposition chamber, and inside the deposition chamber, as you see, the first is the substrate holder, and this substrate holder can hold samples of different shapes and size. This substrate holder can rotate 360 degrees, so it can let deposit at a particular angle. Next part is the infrared heater, and this heater can be used to heat the chamber temperature up to 300 degrees Celsius, and sometimes it is required to get a very uniform thin film. Next part is the thickness monitor. In this thickness monitor, we have quartz crystal monitor, and this QCM gives the amount of material deposited over the QCM. The lowermost part of this chamber is the heart of the system. Inside this heart, there are 4 cavities, and in the 4 cavities, we can put graphite crucibles which contains the target material. So we can deposit 4 different materials in a single sample at one deposition. And inside this heart, there is the tungsten filament from which the electrons are ejected, and these ejected electrons are focused using these 2 electromagnets towards the target material. Once the electrons strike the target materials, it gets started melting and evaporated. The evaporated atoms get deposited on the sample which is put on the substrate holder, and this has to take in a very high vacuum. So we have 2 vacuum pump system attached to this chamber. So I will show the vacuum pumps which is attached in the back side of this deposition chamber. Now let's open the back side of our deposition chamber, and let's see the rotary pump first. This is our rotary pump, and this pump will bring down chamber pressure from 10 to the power 3 millibar to 10 to the power minus 2 millibar. So when the chamber pressure reaches up to 10 to the power minus 2 millibar, the turbomolecular pump will start. So this is our turbomolecular pump, and it can bring chamber pressure up to 10 to the power minus 6 minus 7 millibar. We have to do deposition at 5 into 10 to the power minus 6 millibar. So it takes around 3 hours. So it has the facility of putting liquid nitrogen here. If we put the liquid nitrogen here, then it can take lesser time to bring the chamber pressure to 5 into 10 to the power minus 6 millibar. We need nitrogen gas in order to open our chamber. So we have nitrogen inlet, we have compressed air inlet, we have rotary exit point here, and all this chamber and the turbomolecular pump has to be cooled down using our chiller water. So this is the chill water inlet, and it is maintained at 20.5 degrees Celsius, and this is the chill water inlet, and this is the chill water outlet. Now let's try to understand the different components of our control unit. First is the display. This displays the chamber pressure, and as you see here shows the chamber pressure in millibar inside the deposition chamber. It also has many touch buttons, and this is used to start the process, ban the system, and the whole deposition process can be start from this unit. We have then input output button and then reset button, and this is the emergency stop button. So if there is any mishap during the deposition, we can directly push this emergency stop and can stop all the process at one time. And this shows the status of the safety interlocks, water cooling system, and when the source is enabled, it will glow. Next is the most important part of our control unit. This is just like the brain of our system. This is Inficon SQC310 deposition controller unit. So we have to put the parameters required for deposition in this deposition controller. So I will explain the parameters required for deposition during the deposition time. This is the substrate heater controller. So we can control what temperature should we give in the deposition chamber through the infrared heater. This is for the shutter control. And next portion, this unit is the controller for the tungsten filament, the current and the voltage supplied to the tungsten filament. Next part is the E-beam sweep controller. So we can control the beam's position, size, and amplitude from this control unit. So as you see, there are 4 sweep control units here, 1, 2, 3, 4. Each sweep control unit is assigned to its cavities that we have already shown in the deposition chamber. And on the left, this is the joystick sweep controller. Next part is this crucible indexer. So we can select which crucibles we want to deposit. So this will show the status of the turbomolecular pump. So in the lowermost part, this is the power supply for the control unit, and we have to switch off and on when we want to start the control unit. As we have understand the different components and different parts of our deposition system, let's start deposition. So first, let's put this substrate over the substrate holder. So there are clips which can hold the substrate. We have to put any substrate of any shape and size like this clip, and after that we have to mount the sample holder in our system. So we have to tight this screw using the Allen key. So it can be rotated 360 degree, so we can put at any angle to get the deposition. So let's put 90 degree towards the target material for our deposition. Now let's close the chamber. So we have closed our chamber. So let's start the process here. We have to put the start button here, and it start backing pump. So roughing pump has started. It will bring from 1 into 10 to the power minus 3, 1 into 10 to the power 3 millibar to minus 2 millibar, and after that turbomolecular pump will start. So we have to wait till this process button becomes active. So it will take around 5 minutes. As we are waiting for the chamber pressure to come down to 5 into 10 to the power minus 6 millibar, let's try to put the parameters required for our deposition. So this deposition control has different menus. First is the next menu, process menu, film menu, system menu. First we have to go to the film menu, and here we have to set the name of the materials that we want to deposit. So first choose an empty film menu. We have to push create, edit name. So let's try to deposit silver. So put AG here. This insert small g. So let's save the name. Name has been created. So we have to change the parameters here. Here PID we don't need to change the parameters. For film tooling we have to set it to 65% because the height of the QCM is different from the substrate holder side. So we have to edit it here. We have to change the knob so that it comes to 65%. Next is the pocket. This is the cavity in which we put the graphite crucible with our sample. So we put silver in our pocket number 3. So we have to select it 3. Then we have to select the material, which material we want to deposit. Silver, we have to select the silver material. silver. So here, as you see, automatically density and Z factor has been taken from the database. So next, other factors we don't need to change. Next part is our film conditions. So here we have to set the ramp power. Ramp power is the power which we want to apply to the tungsten filament. So we have to edit it here. First, let's put it 1%. Next is the ramp time. It is the time required to reach this ramp power. So let's say 1 minute. And next is the soak time. Soak time is the time in which this ramp power should remain constant. So let's put 2 minutes. And this soak time is required longer for materials having high evaporation, high melting points. Next is the ramp 2 power. So ramp 2 power should be greater than the ramp 1 power. As we set ramp 1 power to be 1, so let's set ramp 2 power to be 2.5. And similarly, as we did, we will set the ramp 2 power. Let's put 1.5 minutes. And the soak time, let's set it to 2 minutes, similar as in ramp 1 power. So this is done for the film menu. Let's back to the main menu. So film menu we have set. Next, move to the process menu. In process menu, similar as we did for the film menu, we have to set the name of the process that we want to deposit. So here we have to create edit name. So we are going to deposit a single layer. So we can put name silver here also, AG. But if we want to deposit multiple films like silver and gold, then we have to put gold different another name also here. Like this. But right now in our case we are going to deposit silver only, so we are going to put AG only. So let's save the name. We have to select it and then edit. Here we have to choose the film menus that we define already in the film menu. So if we are going to deposit 2 different films, then we have to insert 2 different film menus. But right now, as we are going to deposit silver only, so here we have to insert the silver menu that we have created earlier. So this is the 19th number that we had created earlier. So let's insert it. So this film has been inserted. So one important point here we must have noted for depositing the multiple layer is that the first layer that is going to deposit should be put in layer 1.1 and the second layer will come as layer 2.1. So let's edit the process menu. First is the initial rate. This is the rate of deposition. So let's say 1 angstrom per second rate of deposition. And next is the final thickness. This is the final thickness up to which we want to deposit the film. So let's say 25 nanometer. So we have to set 25 nanometer here. So this is 25 nanometer. Time set point, it is not required in our case. Thickness set point is not required. In this start mode we can do manual and auto mode also, but here we are going to do the auto mode. Here is the sensor. Sensor 1 is the QCM, so we have only one QCM inside the chamber, so we have to on. This is the source 1, or electron beam source. This is the maximum power which we have to supply through the tungsten filament in order to attain this rate of deposition of 1 angstrom per second. So let's put 10%. We don't need to put the minimum power, and slew rate we have to put 0.1% per second. So this is all for the parameters that is required for our deposition. So when the chamber pressure is to 5 into 10 to the power minus 6, we can start the deposition process. Right now the chamber pressure is 6 into 10 to the power minus 6 millibar. So we can start our E-beam gun. So for switch on the E-beam gun, we have to first switch on the electric power supply here, and then we have to switch on the control power, and it is blinking, so we have to wait 3 minutes when it becomes stable. So now the LED for ear cap is stable, so we can switch on the voltage source and the current source. So first switch on the voltage source and then the current source. We can see the chamber temperature here. So right now it is 21 degrees Celsius, and we have switched on the E-beam gun, so we can start our deposition process. So we have to press start here because we have already put the film menu and process menu. So let's start the deposition process. As you see, we have put thin film menu of silver. So first one, it is increasing the power. So I will show the power here. So we can see the next graph. So this is showing the power versus time. So it will start increasing from 0 to 1% as we said in the thin film menu, and it will soak for a certain time. After that it will move to the RAM to power. So right now after the soaking time 2, it starts deposition, and right now the power is 4.7 and the deposition rate is 0.11 angstrom per second. So we can see the rate of deposition graph from using the next graph button. So this is the rate of deposition showing here, and this is the rate deviation versus time. As you can see, this is the thickness of the film that is being deposited. So it's 0.003 kilo angstrom. So let's increase the power so that we can achieve higher deposition rate. So as you see the increase in power, you will see more reddish in the target material also. So the deposition rate has been increased to 0.19%, 0.20 angstrom per second. So let's increase the power. So the rate of deposition is increasing and it becomes almost constant after some time, and so let's wait for some other time because the rate of deposition is start increasing. So the material is being deposited over the sample which is put on our sample holder. So right now our deposition rate is 0.9, it is almost 1. So we can decrease the power a little bit so that it comes to 1 angstrom per second. So right now the film thickness is only 6.8 nanometer. So as we had said, the final thickness of 25 nanometer, when it reaches the thickness of 25 nanometer, the whole deposition process will stop automatically. So let's wait till the thickness reaches to 25 nanometer. As it has been 15 minutes since we stopped our deposition process, let's now open the chamber. So first we have to seal the chamber, and then we have to press the bend button. So here we have to pass the nitrogen gas. So the nitrogen, as we pass the nitrogen gas, the chamber pressure rises. So when it reaches 1 into 10 to the power 3 millibar, we can open our chamber. So we have to wait till it reaches 10 to the power 3 millibar. So as the chamber pressure goes up to 10 to the power 3 millibar, now we can open our chamber and we can remove our sample. This is all the process that we follow for our deposition. This is our silver deposited over the substrate, and it is very uniform, and you can see the silver deposited over the substrate.